surface temperature based on models with natural forcing only. If you remove the humans on the planet, the temperature at various locations on the planet and near the global temperature would behave as in the blue shading here. If models include anthropogenic contributions, so contribution by the humans, we see that the models show that the pink shading, so this is, if we stick just to the global temperature, we see that there's an increase in temperature. And the black line is what is the real observation. So we see that the climate is changing, and the climate is changing notably due to the fact that humans put all of the CO2 in the atmosphere, or greenhouse gas in general, into the atmosphere. Where will it go? Well, in 2010, at the Conference of Parties in Copenhagen, the global community, the world community got together and said, we need to stop the increase in temperature at 2 degrees Celsius. Now, when you look at IPCC data, if you agree that you accept a 2 degrees Celsius increase in temperature, then you can determine what type of concentration of CO2 you can accept in the atmosphere. That's indicated on this graph here. So if we accept a 2 degree increase in global temperature in the atmosphere, this means that we need to have the greenhouse gas concentration in the atmosphere stabilized at around 450 ppm, parts per million. So more and more we're hearing about this concept of the 450 scenario, the 450 scenario. What it means is that we accept that we will stabilize the CO2 the concentration in the atmosphere at 450 parts per million. Now, to achieve that, because CO2 has a life cycle, there's a lifetime of CO2 in the atmosphere, whether it is methane, nitrous oxide, or CO2, lifetime is different, but globally there's a lifetime for every greenhouse gas that we put into the atmosphere. So, in order to achieve a 450 scenario, therefore to stabilize the concentration of greenhouse gas in the atmosphere, well, this is the world CO2 emission of greenhouse gas observed up to the year 2000. But if we want to achieve the 450 scenario and therefore have a 2 degrees Celsius increase in temperature, we need to start decreasing CO2 emission in our activities. So not only stabilize CO2 emission, but decrease CO2 emission in order to sustain or to have a maximum 2 degree Celsius temperature increase into the atmosphere. The science of climate change is relatively strong, and therefore it gives us some good indication that we need to reduce our greenhouse gas emissions. So therefore a conference like this one, where we bring debate and we work towards reducing greenhouse gas emission, is very relevant in the big picture. Another concept here is the correlation between the primary energy demand per capita and the Human Development Index. What this graph shows here is that the more energy is consumed per capita compared to the Human Development Index, we see that OECD countries, which are essentially the developed countries, we see that there's a strong correlation between the high level of Human Development Index, or quality of life in general, and access to energy. The more you have access to energy, the better chance your quality of life will be higher. And if you look at countries with some low access to energy, you see that most of the country has very low Human Development Index. So again, there's a correlation between energy, access to energy, and quality of life. This graph is not from my own research work, but I think it's a graph that tells a very good story. And it's called the waves of innovation. And essentially it shows where the evolution of the innovation process through the years. If you look at it 200 years ago was what is called the Industrial Revolution. We learned how to create mechanical work using coal and with vapor as a transmission for this mechanical energy. And this has changed the world, completely changed the world. And so the innovators at that time, 200 years ago, were the people who would have a conference like this one here would be talking about vapor motor, the Watt engine, creating a movement of a shaft using coal energy. Then came steam power, railroad. And then 100 years ago, we learned about electricity, Maxwell equation in 1897. Electricity and magnetism was explained with the Maxwell equation. At that time, those were the people who were the most advanced in thinking, the most advanced in science, the most advanced in technology. Right now, electricity is a common thing. Then came petrochemical, electronics, aviation, space. 50 years ago, the man went to landed on the moon. Satellites, those were the NASA, those were Boeing, those were the real innovators. Right now, we're in the era of digital network, biotechnology, software, information technology. Those are the whiz kids of the day. Well, what's the next innovation coming? The next innovation coming is related to sustainability, renewable energy, industrial ecology, green chemistry, biomimicry. So essentially, all of the next wave of innovation is related to sustainable development and sustainability in general. So we are part of this movement towards innovating to allow us to have a better planet to live in. I come back to the energy sector. The IEA, I have a few slides with information from IEA, which is the International Energy Agency based in Paris, which advise the OECD countries on various energy policies. So it's really the leading organization in the energy sector. And IEA said 2 years ago that we need a revolution in energy production and energy consumption. To do that, we need to look at a long-term perspective. But there's an urgency of taking actions today. And there are technical challenges to achieve that. We recognize that. We also need to move toward a low-carbon economy, an economy where we reduce our greenhouse gas emission. To do that, we need to restructure energy systems, and we need to develop low-carbon technologies. Still, moving on with IEA, IEA is increasingly working on renewable energy as a secure and long-term supply of energy for the OECD countries and the world in general. So in 2011, IEA published its first, what they call Clean Energy Progress Report. So essentially, IEA now will start tracking the evolution of green energy, renewable energy, as part of the energy mix on this planet. So essentially, in 2011, IEA said that clean energy technologies are making clear progress globally, but fossil fuel continues to outpace them. We're still very dependent on fossil fuel. To achieve sustainable energy goals, we'll need to require doubling of all renewable energy use by 2020. And IEA mentions that biofuels in general, and I'll come back to biofuels in a few slides in a few minutes, biofuels are part of the solution. There's some challenges of using biofuels, but biofuels, bioenergy in general, is part of the solution of moving towards renewable energy and a greener energy system on this planet. IEA also said that we need government policies to be put into place, and essentially by increasing public investments in innovation through large-scale demonstration projects. Demonstration projects are part of the solution, and to develop technology, but also to build capacity, learn, train people, understand these type of systems, how they integrate in the energy portfolio of a country. They also mentioned that we need some smarter energy policies where we remove non-economic barriers and providing transparency to increase the penetration of renewable energy in the energy portfolio of countries. We need to develop smart grids. I'll come back to that. We need to phase out subsidies for fossil fuel, and once those subsidies will be phased out, fossil fuel will decrease in terms of utilization. And IEA is advocating to put a price on CO2 emission. So this, when there will be a price on CO2 emission, it's going to be a real game changer in the energy sector. And the countries who are not adapting their energy system for eventually a tax on carbon or a price on CO2 emission, these countries will suffer very strongly if they're not prepared to do that. So that's a global picture of the energy sector. Now I'll talk about various renewable energy that's available and some of the work that we've done. and hopefully this will inspire you here in Thailand. This is a map of, well, two maps of Denmark. So on the left here is a map of Denmark corresponding to the energy production in the 1980s. So Denmark is here, so Denmark is attached to Germany, so Germany is down here. You have Norway up here, Sweden up here, so Denmark is a small country in Northern Europe. The dot on this graph here represents an energy generation site in Denmark. So a place where electricity is generated. And the larger the circle on these two maps, the larger the unit of generation. So we see that in the 1980s, most of the energy in Denmark was generated locally, centralized energy distribution with big systems. If you look on the map on the right, which is still Denmark, but in 2008, what it shows is Denmark has moved from what we call the centralized power generation to a distributed power generation system. And you see that the circles are much smaller. So each point of generation of electricity is much smaller than it used to be in the past. Why is it? It's because it is based on renewable energy. In Denmark, this renewable energy is mostly wind energy, but also biomass energy. Agriculture waste in particular, biogas also. This is a map of Austria. On this map, the small circle is what is called a district heating system. So essentially a centralized heating system where the hot water or steam is transported from one to many buildings. So you have one site of generation of heat, in this case heat, and the heat is transported to heat many buildings all around. The larger circle is what is called a CHP, combined heat and power. So again, you have a system that generates heat. You start by extracting some of the energy from that heat by generating electricity, and the remaining heat you send it to heat some building in the city. But what's interesting here is that all of these dots in Austria, whether it is for district heating or electricity generation, combined heat and power, is based on biomass. And in this case, wood and forest biomass. So you see that we've got, this is a model of two countries that are developed countries, OECD countries, that rely strongly on distributed power generation for the electricity based on renewable energy resources. So what is distributed power generation? Essentially, it is a small modular electricity generator sited close to customer load and also close to where the fuel is. And in this case, it's a fuel that is the wind, small hydro, biomass, tidal power, etc. So it's a fuel flexible system near consumers. By doing that is you capitalize on the availability of a renewable energy source that is locally present somewhere. You avoid transmission over long distance of electricity, and you minimize your transmission and distribution losses in doing so. But fundamentally, it allows you to exploit a small source of energy. You don't need big generation site. What you need to do is go to find where there's some energy locally and exploit that energy locally. Some drivers of distributed power generation, well, it's government policies, whether to tax credits, tax incentives, what we call renewable portfolio standards, which is a minimum of renewable energy in the energy portfolio of a jurisdiction. Some form of feed-in tariffs, so a special rate for energy generated from renewable source, permitting process, grid interconnections, environmental attributes, etc. The price of fossil fuel is also a driver for its development. I've showed you two examples, Denmark and Austria, where distributed power generation is highly present. Well, if you look at the map of Europe, and if we concentrate here on the circles, the red circles, you see that on the scale here, this is the percentage of the energy in those countries coming from distributed power generation based on renewable energy, wind, biomass, small hydro in particular. So you see that countries like Denmark have between 25 and 30% of their energy coming from distributed power generation. Other countries like Netherlands, Germany, Spain, Portugal have between 20 and 25% of their energy coming from distributed power generation. Usually electric utilities, they like to have big systems, coal, oil-fired, big dams. What this graph is saying here, well, yes, we need some of those big energy generation systems, but we also need to capitalize on small systems, on smaller systems, where you have based on renewable energy. And it's part of the energy portfolio. It should be part of the energy portfolio of a jurisdiction. If you look at wind energy, this is the world installed capacity at the end of 2011. What we see here is that globally wind energy is total installed capacity of 238,000 megawatt. For sake of comparison here, I think that Denmark, the total capacity of Denmark is around 30,000 megawatt of installed capacity. All sources of energy included. So there's 8 times more wind energy alone around the world compared to what is generated in Thailand. What this means is that wind energy is a mature technology. Wind energy is an important source of energy for many, many countries around the planet. We see that if you look at China, China 2 years ago became the #1 wind energy producer in the world when they passed the United States and Germany. So the total capacity in China of wind energy alone is 62,000 megawatt. So there's 2 times more wind energy in China than all of the energy generated in Thailand. It's huge. Last year, 42,000 megawatt of wind energy was installed around the world. About half of that was installed in China. Last year we saw China coming into the market with turbines. Up to 2 years ago, turbine manufacturers were dominated by European companies, mostly from Denmark and some from Germany also. But since 2 years, China is now offering some turbines on the international market. And they are offering a very good price, and they even finance their own turbines. That's how aggressive they are. China will most probably in the next few years dominate the wind turbine market around the world. Wind farms are nice. We do a lot of work on wind energy. This is what I would call a large onshore wind farm, where you see that the land is used by agriculture, but there's some wind turbine installed. But you still do your agriculture on your land. This is a smaller system where you have only 2 turbines. This is called community energy. I will come back to the concept of community energy a little bit later on. Where a wind farm in this case is owned by the community, by a municipality, a cooperative, and that's also very interesting. And we have offshore wind farm. This is a huge one in Denmark, orange red, where you have a better wind, but it's more costly to install. This is my province on the east coast of Canada. So this is the Atlantic Ocean here. This is the United States. So this is really the end of Canada on the right side, on the east side. When you look at the map, touching the Atlantic Ocean. That's my province here. So we've done a lot of work on what is called wind resource mapping. So essentially we publish this map, and so that we identify the best location to install a wind farm. And in this case, everywhere that's yellow and orange and red are good locations to install a wind farm. In my province, and we've done many other provinces in Canada, but I'm only going to talk about my own province, New Brunswick. When we published this type of map, it made some real significant changes within government to adopt wind energy as a source of power for our province. We've started to do some work with Professor Jumbo out of Taksim University in Patalong campus. And so this is the wind atlas of southern Thailand. So we see that in southern Thailand there are some good locations to install wind farms, notably in zones of elevation here. This is the province of Nakhon Si Thammarat and Songkhla provinces in Thailand. So you see that there are some opportunities here in Thailand, but ideally we would make the wind resource map of the whole country of Thailand, and hopefully we'll be able to do that in the next few months or years. There's also small hydro, what we call small hydro, some various name, micro hydro, mini hydro, small hydro, but essentially it's a hydroelectric project that takes advantage of a small hydro resource, whether it is a small river, small head, and you can use what is called run-of-the-river technology or low-head technology. It exists, this is an example in Netherlands where you have 100 kilowatt, a small hydro system that uses a river to generate electricity, but on a small scale. This is one in the state of New York, where we use what is called a run-of-the-river. So you see there's no reservoir, there's no perturbation upstream of the river. You really use the current of the river as your source of power. So, but what it shows is that this type of technology exists and should be part of an energy mix. We recently published with the government of my province what we call small hydro potential in New Brunswick. So we've developed some methodology where we identify locations where we could install some small hydroelectric projects throughout the province, and the circle is based on the size, the capacity of that project. So essentially what we're hoping will happen is that some investors or community